Imagine you sit down to watch a movie, but instead of actors and dialogue and, crazy car chases, you are just staring at a pink, fleshy wall.
Oh, that sounds awful.
Right. And it's for 37 hours straight. If you blink, if you zone out for even a fraction of a second, you might miss a single 1-second visual clue. And missing that clue, well, that could be the difference between catching a life-threatening illness early or letting it slip by completely unnoticed.
I mean, it sounds like some kind of psychological torture, honestly.
Oh.
But what you're describing is actually the daily reality of clinical medical review.
Yeah, exactly. And, we hear all these incredible stories today about artificial intelligence. You see these viral clips where an AI tool ingests a massive 2-hour blockbuster movie and, instantly summarizes the plot.
Right, it gets all the character arcs.
Yeah, it picks up on the action scenes, the twist ending. It feels like magic. But today's deep dive is really about what happens when we take that exact same state-of-the-art AI and we basically force it to stare at that pink wall.
Which is exactly what a fascinating new research paper set out to do. They built a benchmark called MedHorizon to test this very scenario. Because the assumption most people make is that, video is just video.
Right, if you can watch YouTube, you can watch surgery.
Exactly. If an AI can track a complex bank heist in a Hollywood movie, surely it can track a camera moving through a digestive tract. But today, we're going to explore why that assumption is fundamentally and, frankly, dangerously wrong.
Because the stakes here are just massive. I mean, when we talk about clinical AI, we aren't talking about a neat little parlor trick. We are talking about finding the exact right, subtle piece of data when a patient's life is literally on the line.
Yeah, the consequences are vastly different.
Like if an AI misses a plot hole in a movie summary, it's a funny meme. But if it misses a subtle mucosal lesion during a surgical review, I mean, that is a catastrophic failure.
And to understand why this is so incredibly difficult for a machine, we really have to look at how the authors lay out the core challenge. If we look at section 1 of the paper, they point out that in a normal, natural video, like the ones these AI models are constantly trained on, the evidence you are looking for is what they call temporally dense and spatially salient.
Wait, temporally dense and spatially salient? Break that down for me. You mean like a soccer player scoring a goal?
Yeah, that's a perfect example. A soccer goal takes up the whole screen, right? It's visually distinct from the grassy field, the crowd is cheering, and the action happens over several seconds. It's obvious.
So it's hard to miss.
Exactly. But in medical procedures, decisive medical evidence is the exact opposite of that. It is temporally sparse, it's spatially subtle, and it is highly context-dependent. Like a lesion might just be a tiny discoloration that flashes on screen for half a second while the camera is quickly moving.
Right. And the researchers give us a really stark visual for this. In Figure 1A, they explicitly compare these natural videos from standard datasets with medical videos. And the medical footage is characterized by what they term highly homogeneous anatomical appearances.
Which is a very fancy way of saying it all looks the same.
Yeah. Basically, to an AI, one frame of the intestinal wall looks exactly like the frame before it and exactly like the frame 10 minutes after it.
It is a total sea of visual redundancy. And what is truly fascinating is how they actually quantify that monotony. Looking at Figure 1B, they drop this statistic that is just staggering. The videos in the MedHorizon benchmark contain only 0.166% evidence frames on average.
Well, wait, let me make sure I heard that right. 0.166%.
That breaks down to just 1.7 frames per 1,000 frames.
1.7 out of 1,000. And, the paper notes that this is 169 times sparser than the general AI video benchmarks that all these tech companies usually use to brag about their models.
Yeah, it's a completely different league of difficulty.
So looking for clinical evidence in a video isn't like finding a needle in a haystack. It's more like finding a needle in a massive stack of slightly duller needles while staring at the exact same pink wall for 3 hours.
That is the perfect analogy, honestly. And remember, that single dull needle might be the absolute only indicator of a developing pathology. So the challenge is not merely the length of the video. The really fatal combination for the AI is extremely sparse evidence hidden within overpowering visual redundancy.
Okay, so existing general AI benchmarks just totally fail to simulate this needle in a stack of needles problem. So how do researchers actually test if an AI is ready to be used in a real clinic?
Well, this is where the MedHorizon dataset comes in. They needed a true stress test.
Right. And according to Section 3, the authors detail the sheer staggering scale of the dataset they built. We are talking about 759 hours of raw clinical procedures.
It's massive. 340 videos across 7 different organs.
Yeah, and it encompasses both diagnostic examinations like an ultrasound and full surgical workflows. And some of these procedures last up to 37.2 hours.
Yeah, that's a very long time for a machine to pay attention.
37 hours. Now, hold on. I have to push back here for a second. If the videos are up to 37 hours long, Why don't researchers just, do what they do on social media, chop it up?
Right, the TikTok approach.
Exactly. Why not cut that 37-hour surgery into bite-sized 30-second clips to make it way easier for the AI to train on and understand? Why force it to watch the whole exhausting thing?
I mean, it's a very tempting shortcut. But if we connect this to the bigger picture of clinical medicine, the reality is that real clinical review is inherently process level.
Process level, meaning what exactly?
Meaning you cannot judge the quality of a bowel prep or ensure an ultrasound technician hit all the required standard views by just looking at an isolated 10-second clip.
Oh, I see.
In the real world, a doctor has to track the entire procedural withdrawal phase or surgical workflow from start to finish. If you chop the video up, you destroy the timeline. You completely destroy the context.
Ah, okay. Because if I just see a 10-second clip of a scalpel making a cut, I don't actually know if that cut is happening at the right time or if they skipped 3 crucial steps beforehand.
Precisely. And Table 1 shows that this requirement is exactly what makes MedHorizon unique. If you look at Table 1, the authors compare MedHorizon to older medical video benchmarks. MedHorizon is the only one in that comparison that tests the combination of full procedure context, extremely sparse evidence, and multi-hop reasoning.
So the older ones just gave the AI the easy parts.
Yeah, most older tests just give the AI a short pre-trimmed clip where the important thing is already happening right in the center of the frame. MedHorizon forces the AI to do the retrieval before the reasoning. It has to actually search the noisy, hours-long stream first.
Retrieval before reasoning. I love that phrasing. It basically has to find the homework before it can actually do the homework.
Right, and it's really hard homework.
Yeah, and the complexity of that homework is mapped out beautifully. Figure 5 explains the capability hierarchy they designed. They break down the difference between what they call fine-grained understanding and semantic reasoning.
Yes. So fine-grained understanding is the foundational level. Can the AI locate a specific anatomical region or recognize an instrument entering the frame? It is relatively local.
Okay, that makes sense.
But semantic reasoning, specifically multi-hop tasks, is where the cognitive load becomes massive.
Right, and semantic reasoning sounds a bit like a Silicon Valley buzzword, honestly. What does a multi-hop task actually look like if, say, I am a patient on the operating table?
Let's walk through a visceral, step-by-step clinical scenario to picture it. Imagine a patient is getting a full colonoscopy. A multi-hop task requires the AI to first scan the entire hour-long video. Hop 1. Identify every single potential lesion as the camera flies by.
Okay, so find all the bad spots.
Yep. Then, Hop 2. Bind each of those lesions to its specific anatomical segment, meaning the AI has to know, I saw this shadow in the rectum, but I saw this other shadow in the cecum.
Which is important because a lesion in one part of the body might require a totally different surgical approach than a lesion in another, right?
Exactly. Then Hop 3, the AI has to count them all up. And finally, Hop 4. It has to compare those counts mathematically across the entire procedure to tell the doctor which specific segment had the maximum cumulative frequency of lesions.
Wow. So it has to find multiple needles, remember exactly where each needle was found, categorize the needles, and then do math on the categories, all while the camera is just constantly moving.
Yes, it is a massive cognitive load.
So we gave the world's most advanced AI models this ultimate medical stress test. How did they actually perform?
Let's just say the AI did not pass its medical boards.
Yeah, Table 2 reveals a pretty grim picture. The overall results are honestly shocking. The absolute best model they tested, which was Gemini 3.1 Pro Preview, a cutting-edge corporate AI backed by billions of dollars, it scored only 41.1% overall accuracy.
Which is very low.
Yeah, and most of the open source models, like the Quinn series, which are basically the free, publicly available AI brains that developers use, they were stuck way down in the mid-20s.
Right. And keep in mind the structure of the test here. A lot of these questions are a 4-way multiple choice.
Oh, wait, so...
Yeah, so a completely random guess, just throwing a dart at a board, would get you 25%. Many of these incredibly sophisticated multi-billion parameter models are essentially performing at the exact level of a random guess when they're forced to look at the full clinical context.
That is wild to me, all this hype in the news, and it's basically just guessing C on the Scantron. But here is where my mind was truly blown. Under Section 4.3, specifically Research Question 2, they ran a fascinating experiment to figure out why the models are failing so spectacularly.
Right, because you have to ask, are they failing because they can't find the evidence, or because they just don't understand it once they do find it?
Exactly.
This is the absolute crux of the issue. The researchers designed what they call an oracle experiment. They bypassed the retrieval phase entirely. They manually handed the AI the exact human-verified frames where the crucial clinical evidence was located.
So they cheated for the AI.
Basically, yeah. They said, here, we found the needle for you. We paused the video right on it. Now tell us what it is.
And looking at Section 4.3, even with those oracle frames, the accuracy still stayed below 40% for the models tested in that specific breakdown. Wait, let me make sure I'm wrapping my head around this. You're telling me that even if you hand the AI an open book with the exact right paragraph highlighted in neon yellow, it still gets the answer wrong over 60% of the time?
Yes.
How is that even possible? What on earth is happening inside the AI's brain?
Well, it proves that retrieval is only the first bottleneck. Even when handed the evidence on a silver platter, the AI deeply struggles with visual interpretation in a medical context. It still has to identify incredibly subtle findings and distinguish between very similar-looking anatomical structures.
Right. It doesn't just automatically know what it's looking at.
Exactly. Just because it's looking directly at the lesion doesn't mean it has the clinically grounded visual knowledge to recognize it as a lesion, rather than just, a normal shadow or a fold in the tissue.
Okay, so handing it the right frame still results in a massive fail. That sets up the why perfectly. Because the problem isn't just about finding the evidence, it is about how the AI fundamentally thinks about what it is seeing over the course of time.
Exactly. And the paper exposes a really fatal flaw in how these models process temporal structure, meaning how they understand time passing in a video. In Figure 8, the researchers detail a frame shuffling experiment.
Frame shuffling.
Yeah, they took the medical videos and completely scrambled the order of the frames. They reversed them, they shuffled them locally, they totally broke the timeline.
And what happened? Because if you took my favorite movie and you put the ending in the middle and the beginning at the end, I would be completely lost. I wouldn't know what was going on.
You would be, yes.
Will you?
We all would. But surprisingly, the AI's performance barely dropped at all. For instance, the Qwen3 VL8B model only dropped from 26.5% accuracy to about 24.2%.
Wait. If shuffling the video doesn't break the AI's performance, that means the AI wasn't actually paying attention to the timeline to begin with.
Spot on. It mathematically proves the AI isn't actually using procedural chronology. It has absolutely no real concept of a workflow timeline.
That's crazy.
It is just treating the video as a big bucket of independent photographs, reaching in and trying to grab coarse visual cues without understanding the sequence of events at all.
That is a huge blind spot. For something like surgery, the order of steps is literally the whole point. You can't stitch the patient up before you make the incision.
Right, the sequence is everything.
But the researchers go even deeper than that, right? Because they also looked at where the AI was actually focusing its digital eyes during these long, repetitive procedures.
Yes, and this is where we really get into the mechanics of how these models fail. Figure 9 introduces this critical concept of attention drift. The researchers analyzed the attention distribution of the transformer models.
Okay, let's slow down for a second there. When an AI pays attention, what does that actually mean under the hood? It doesn't have literal eyeballs scanning a screen.
That's a great point. Under the hood, these AI models use a mathematical matrix to assign a weight or an importance score to every frame they process. In a normal video, when something important happens like a car explosion, the math spikes sharply. The AI assigns a massive weight to that one moment.
Okay, so it highlights the explosion.
Right. But in these medical videos, because of the strong spatial and temporal redundancy, remember the 30 hours of the pink wall, the AI's attention mechanism breaks down. It smears.
It smears, like wiping wet paint across the canvas.
Conceptually, yeah, exactly like that. It diffuses across all those visually repetitive, clinically non-decisive frames. Because the frames mathematically look so similar to the AI, with frame similarity scores hovering around 0.90, the model's mathematical weights just flatten out. The attention drifts.
Oh, I see.
Instead of hyper-focusing its computing power on the one subtle outlier frame that actually contains the lesion, it spreads its attention thinly and evenly across hours of completely normal, healthy tissue.
It sounds exactly like a tired student studying for a massive final exam. They are just exhausted, so they start staring blankly at the wallpaper because it happens to be the exact same color as their textbook.
That's hilarious, but true.
They are looking, right? Their eyes are open, but they aren't actually seeing anything.
That is a very accurate way to visualize it. The medical redundancy is deeply, deeply deceptive to the architecture of current AI. The model mathematically thinks, oh, I've seen this before, I'll assign weight to it again. But it ends up paying attention to the wrong things simply because there are so many of them. The sheer volume of the pink wall just grounds out the signal.
So if the video is mostly repetitive wallpaper that confuses the AI and causes this huge attention drift problem, my immediate thought is, why are we making the AI watch the whole thing at normal speed? Why not just program the AI to fast forward? Can't we give it a smart sampling strategy so it skips the boring parts and only stops when something actually happens?
It is a highly logical next step, and the researchers explored this exact idea. Section 4.5, Research Question 4, discusses how they tested various generic sampling strategies to see if they could fix the drift problem. But they ran into a fatal trade-off.
Let's walk through those strategies. What happens if you use uniform sampling? To use a non-medical analogy, uniform sampling is like taking a photograph out of a moving train's window exactly every 10 seconds, right?
That is a brilliant analogy.
Aye.
Yes, uniform sampling skips ahead at a set, steady pace. You take a snapshot every few seconds to build a summary.
Sounds efficient.
It is, but the problem is, as we established earlier, clinical evidence is extremely sparse. If a lesion is visible for only a fraction of a second as the camera pans by, your 10-second train window snapshot is almost guaranteed to jump right over it.
Oh, right.
You preserve the timeline of the train journey, but you completely miss the split-second lightning strike outside the window.
Okay, so taking pictures on a timer is out. What about change-focused sampling? Staying with the train analogy, this would be like only taking a photo when the train changes tracks, or when the scenery drastically shifts from a dense forest to a big city.
Right, so change-focused sampling helps a little bit with finding local details, but it completely loses the long-term context. In a medical procedure, a massive visual change isn't always clinically relevant.
Wait, really? Why not?
Well, the screen might drastically change simply because the camera bumped into the tissue, or the lens was getting washed with water. Conversely, a critical clinical phase, change, like a surgeon moving from one really delicate step to the next, might happen with almost no visual dynamism at all.
Oh, wow.
The train might be going straight for hours while crucial things are happening inside the cars.
Wow. So visual change absolutely does not equal medical importance.
Exactly. Go back to Table 2, the researchers do note that highly specialized long video samplers algorithms like VLAMP and WFSSB, which are designed specifically to compress video while keeping keyframes intact, they do show some modest improvements.
But I feel like there is a but coming.
A big one. Even these advanced samplers completely fail on tasks that require global procedural continuity. They might help the AI identify a specific surgical site slightly better, giving it a microscopic view, but they cripple the AI's ability to do multi-step aggregation.
Right.
They destroy its ability to hold the whole timeline in its head, like counting those lesions over an hour.
It is that fatal trade-off you mentioned earlier. You either get the local detail but lose the global story, or you get the global story but totally miss the crucial local details. You just can't have both with current AI architectures.
No, you can't.
So if we step back from all the data, the tables, and the specific algorithms, what does this actually mean for you, the listener, and the future of going to the doctor? What does the MedHorizon benchmark ultimately tell us about where we are?
It tells us that we need to aggressively separate the hype from the reality. Just because an AI model can process a massive amount of text or perfectly summarize a highly salient, action-packed YouTube video does not mean it is ready to be a reliable, unsupervised doctor's assistant in a real operating room.
The real world is just too messy.
Yeah, current AI architectures are fundamentally misaligned with how medical visual evidence actually works in the real world.
So what has to change? How do we fix it?
To truly succeed, future AI needs to develop evidence-aware temporal retrieval, meaning it needs an architecture that inherently knows how to search for a needle in a homogeneous environment without its attention drifting away. And it needs genuine procedural reasoning so it actually understands why that needle matters in the chronological sequence of a surgery.
It proves that true learning, especially in medicine, is about connecting the dots over time, not just gathering them in a messy pile and guessing C. And that leaves us with a really provocative thought to ponder. Throughout this deep dive, we've talked about how AI struggles so heavily with attention drift. When faced with monotonous, visually repetitive, hours-long medical procedures, the machine mathematically zones out. Its focus smears.
Which is exactly what the frame weighting data proved.
But think about that for a second. How does that compare to the human beings currently doing this job? Human fatigue, zoning out, and attention drift in the clinic are very real, well-documented biological problems. Doctors are staring at those same hours of pink walls. They get tired, they blink.
It is a profound vulnerability in our healthcare system. We are currently seeing the machine struggle with the exact same monotony that plagues human cognition.
Exactly. So could it be that this AI weakness is actually pointing us toward its greatest future strength? If researchers can use benchmarks like MedHorizon to finally figure out how to solve attention drift in the algorithms, if they can build an AI that maintains perfect, razor-sharp focus on the 36th hour of a procedure without ever getting bored by the wallpaper,
That would change everything.
we won't just be matching human doctors. We will be unlocking a level of superhuman medical vigilance that has literally never existed in the history of medicine.
It is a paradigm-shifting possibility. Overcoming the pink wall could completely redefine patient safety.
So the next time you hear about an AI summarizing a blockbuster movie in 3 seconds, just remember, the real magic won't be in a machine that understands a scripted explosion. The real magic will be the day the AI can watch a dark, blurry, repetitive video of a clinical procedure and never once take its eyes off the screen.